Welcome. Let us begin with a review of differential equations. Now, most likely you've already seen differential equations in your calculus classes, in particular Calculus 20D. What we remember from our calculus classes is that a differential equation is an equation in an unknown function that involves the derivatives of that function. It is called a differential equation because, well, it involves the derivatives of the unknown function. The differential equation at the center of the screen reads y prime of x equal cosine of x times y of x. Now, in that equation, the unknown function is y, and y depends on the variable x. What this differential equation tells us about the unknown function y is that the first derivative of y at x, at any x, is the same as the cosine of x times the function y of x itself. Now, in particular, the solution to a differential equation is a function. In this case, the function is called y. And a formula for one possible solution to that differential equation is given at the bottom of the screen. So one solution is y of x equal exponential of sine of x. In order to check that this is indeed a solution, one thing we can do is just calculate the derivative of this y of x. What we get is y prime of x. Well, we can use the chain rule here to the right-hand side of the solution, and we get exponential of sine of x. Now take the derivative of the exponent, which is cosine of x. And we see, well, exponential of sine of x, of course, is our function y of x itself. In this video, we are going to go over a few examples for differential equations, starting with very basic differential equations and then progressively going to more complicated ones. What we are going to see is that some differential equations have solutions that can be written down with explicit formulas, but these formulas, as we're going to see, can sometimes be fairly complicated. In fact, some of them are quite a beast to write down. Fortunately, we are not as much interested in explicit formulas for differential equations here in this numerical analysis class. Instead, we're interested in finding methods to approximate solutions to differential equations. Nevertheless, it is a good idea to have explicit formulas for a few prototypical examples of differential equations in our toolbox. As you might remember, differential equations have many applications in modeling in the sciences. These sciences range from physics, engineering, even sociology. For example, in physics, you might be interested in modeling heat conduction. If you've got, for example, a heated body, then it's going to evaporate heat. For example, if you throw a hot piece of iron into cold water, then the iron is going to cool down, and the rate of heat transfer from the iron into the water can be described by a differential equation, where the function is the heat of the iron. Another famous example, which actually might be the origin of differential equation, is celestial dynamics. If you've got planetary bodies in the solar system, for example, let's say the sun, moons, planets, of course, asteroids, then the movements of these bodies can be described by differential equations. So in that case, typically we are only interested in gravity between the celestial bodies, and that leads to a differential equation, which was first developed by Newton. Other examples are in biology. For example, currently many people are interested in epidemiology, So in fact, during this class, we will talk a bit about differential equations that describe the number of how the number of infected people develops when there's an outbreak of a disease. In that case, the number of infected people is the function that we're interested in, and this function depends on time. So, and we want to understand how does the number of infected people evolve over time. Other examples that are surprisingly similar, for example, consider the spread of information. So in sociology, there are models that describe how information spreads throughout social networks. In fact, the spread of information is very similar to the spread of diseases, however one may interpret that. And if we talk about physics, we can also talk about structural engineering. So there are many differential equations that are used to model, let's say, the behavior of buildings under load. For example, if you have a building, you would like differential equations that describe how it bends if there's, for example, a constant wind, or if there's energy from an earthquake. So there are lots of different applications of these, and throughout this quarter we give many examples of differential equations. And for the beginning, we also talk a bit about modeling. So we will discuss, given some description of processes in physics or biology, we will ask how to develop differential equations from those. Okay, let's take a look at a very simple example of a differential equation. In fact, this example is almost completely trivial. Namely, we're looking for a function, y, and what we know about this function is that the first derivative of y equals g of x, where g is some function. And it's not difficult to guess what is the solution of this differential equation. In fact, there are many solutions that only differ by an additive constant. So all solutions to this differential equation, in fact, look as follows. Namely, the function is y of x equals the integral from 0 to x of this function g. And then there's some additive constant, which we here denote by c. So this differential equation has, in fact, many different solutions, only depending on this constant c. As you might remember, this class of solution here is also called general solution to a differential equation. And in order to get from a general solution to a particular solution, in order to get a unique solution to fix this constant c, what we typically need to do is to fix the initial condition. So for example, I have this function y of x. I know it satisfies this differential equation. And if I say, okay, at x equals 0, this function should assume some value, y naught, then this is sufficient to fix this constant c. Namely, at x equal naught, this integral here vanishes, and the only thing remaining is this constant c. If we say at y naught equal y at 0 equal y naught, in that case we can just say, okay, this constant c can be fixed to y naught. So let's do an illustration of that. Let's say I have the differential equation y prime of x equal, let's say, 3x to the square. What is the solution to that differential equation? What is a general solution to that differential equation? Well, the general solution looks like y of x equal, well, x to the 3 plus some integration constant c. if you want some particular solution, okay, we can say at x equals 0, we have, for example, the value 5. And the result is that the particular solution with that initial condition is y of x equal x cubic power plus 5. As you might have noted, this differential equation is particularly simple because actually it just amounts to computing an integral. That is actually the reason why we often talk about integrating a differential equation, even though we actually do much more complicated things than computing integrals. So one example of something slightly more complicated is the following differential equation. Let's say I'm looking for a function y of x, and I know that the derivative of the first derivative of that function y of x is the same as alpha times y of x, where alpha is just some number. It could be 1, 2, maybe even 0, maybe 1000, pi, whatever. And the general solutions to that differential equation look as follows. Namely, we have got y of x equal c times e to the alpha x. In that case, again, c is an integration constant. This is a general solution. And in order to fix initial conditions, we say that, okay, at x equals 0, the function y should assume the value y naught. And in that case, well, y of x should be the same as, well, what should it be? At x equals 0, we have exponential of alpha times 0. So this term here at x equals 0 is actually just 1. So this is sufficient to fix c. And we have exponential of alpha x here. Let's again do an illustration. So for example, if we've got y prime of x, let's say is the same as minus 5 times y of x. If that is a differential equation, then the solutions look as follows. You've got y of x equal c, which is the integration constant, times e to the minus 5x. Now, if we fix some initial condition, for example, let's say, just for simplicity, at x equals 0, the function y should assume the value just 1. And y of x is just the same as e to the minus 5 of x. Now, such a differential equation is again very, very simple, but it's also sort of prototypical. So quite often when we talk about some simple examples of differential equations, usually the exponential function appears, particularly in the case if we talk about linear differential equation. The exponential function is going to appear sooner or later. And well, such differential equations describe, for example, processes in growth or decline, for example, population growth, or maybe shrinking populations. If you've got a radioactive material, then such differential equations describe how the material decays. And in course of also in epidemiology, you have such differential equations. Now, we go from simple examples to more and more complicated examples. The next more complicated example is the following. Let's say I've got the function y prime of x equal alpha times y of x plus beta. So the unknown function again is y of x, and the first derivative of y of x is alpha times y of x plus beta. So the only thing that's changed from the previous example is this term here, beta. Now, what is the solution to that? If beta equals 0, we just have the same example as before. So we guess that our solution, at least our general solution, will look kind of similar. Now, the solution now looks slightly more complicated than in the previous example. So what we sort of recover from the previous example is this term here, c times exponential of alpha x, where again c is the constant of integration. And now this new term here, beta over alpha times exponential of alpha x minus 1. Now let's check that actually the solution, that y of x is actually the solution to the differential equation, which at first looks a bit scary, but actually it's fairly simple. One good idea is the following. Let's first compute the derivative, y prime of x. So what we have there is then still beta over alpha, and then, well, alpha times exponential of alpha x. The constant term corresponding to minus 1 just vanishes. And then we have c times alpha times exponential of alpha x. Okay, on the one hand we have that. Now, does this look any similar to the right-hand side? Well, let's simplify a bit. We've got beta times exponential of alpha x plus, well, still c times alpha exponential of alpha x. Now the trick is, now to check this corresponds to the right-hand side of the equation, what we can do is just compute the right-hand side of the equation. So let's write down the right-hand side of the equation and just plug in the value of y of x here. So this thing is the same as, well, beta times exponential of alpha x minus 1 plus, well, alpha times the constant of integration times exponential of alpha x, and eventually plus beta. Now we can see that actually we can distribute beta over the difference here, get beta times exponential of alpha x minus beta plus alpha c times exponential of alpha x plus beta, and canceling out these minus beta and beta, what we get is beta of exponential of alpha x plus alpha times c times exponential of alpha x, which, wow, is the same as y prime of x. Now what happens if we fix the constant integration here? Well, it's not hard to guess. The particular solution looks as follows: beta over alpha times exponential alpha x minus 1 plus y naught exponential of alpha x. Now all the examples we've seen so far involve differential equations with constant coefficients. But in fact, most differential equations that appear in physical modeling have coefficients that depend also on the variable x. So a differential equation where the coefficients depend on the variable x looks as follows. You can say, okay, the first derivative of our unknown function y of x should be the same as some function a of x times the function y of x itself plus the function b of x. It will become very difficult to guess a solution for this differential equation. So let me just write it down here. So the general solution to the differential equation looks as follows. Well, I've just written down the solution. And the solution might look daunting at first, but actually, let's just go over it. So y of x is the same as take the exponential of the integral of from 0 to x of the function a of t del t multiplied by the integral from 0 to x of the function b of t times the exponential of minus the integral from 0 to t of the function as ds. Now takes that entire thing and takes integrated over t, and then corresponding to the factor of integration, we have this additional term here, c times exponential of the integral from 0 to x of a of t del t. Before anybody asks, no, I do not expect you to memorize this formula completely. Now, in order to check that this function y of x actually satisfies the differential equation, the best thing we can do is, to start with, just compute y prime of x, given this formula here. So what we do is, we have y prime of x, and, well, here essentially we have a product. Namely, on the one hand, we have the exponential of this integral, and we have this integral here itself, which is a function in x. Now, for this product, we can just use a Leibniz rule. Both of these two factors here are functions in x. For the first factor, okay, we have the exponential function and we compute the derivative of this integral. And that's actually fairly simple. What we get is exponential of, again, the integral from 0 to x, a of t del t, multiplied by a of x, which arguably is quite simple. The second factor stays the same. Now, using the Leibniz rule, let's take the first factor, which this time does not change at all. We don't take the derivative of that guy. But we take the derivative of the second guy. Well, in fact, that's fairly simple. You've got b of x times the exponential of minus 0 and minus integral from 0 to x as ds. And back here we still have this factor of this integration constant, c times a of x times the exponential from 0 to x of a of t del t. So what can we do about this? The first term here that we have computed, this is essentially just a function y of x itself, apart from the integration constant. And the only thing that has actually changed is now this additional term ax. In the second line, okay, we have the exponential of the integral from 0 to x of at del t times b of x times exponential of minus integral from 0 to x of as ds. Now we can just rename this s here to t, and what we see is that these two terms here, well, here we have plus integral, here we have the same integral with a minus. These two terms cancel out. So now it's actually already evident that this is precisely the right-hand side that we want. We have the function y of x, including this factor of integration here, times a of x. And below here, these two factors here cancel out, so what remains is v of x. Voila, everything works out. And we check that if we just plug in y of 0, essentially then this integral here, the second factor vanishes. So the only thing that remains then is c times the exponential of the integral from 0 to x of some function a. But again, this is just c times e to the 1. So again, if we want, let's say that y naught is equal some specific value, then we just set c to that specific value, and we get a particular solution from this general solution. Now, what that example shows us is that the solutions to differential equations, even if we have got explicit formulas, can be quite complicated. In fact, throughout this class, we will not be too focused on explicit solutions to differential equations, but rather we will be interested in approximating these using numerical methods. Nevertheless, of course, if you've got some simple examples of differential equations where you can write down the solution explicitly, that's not only interesting from a mathematical perspective, but also, for example, if you would like to test a numerical method. It's really good if you've got actually an explicit solution to the differential equations that you want to investigate. I mean, for the more complicated differential equations, you probably will not have an explicit solution. So after this, let's do a short summary. So differential equations are equations in an unknown function and its derivatives. And typically what we want is to find this unknown function. Let's say in pure mathematics, we're interested in finding an explicit formula for that function. And in numerical mathematics, we are satisfied if we just can approximate this function. In fact, the solution, just to repeat that, is a function. And that function is a solution if it satisfies the differential equation everywhere, which in this context means for every x. As already mentioned, and as you probably already know, equations have lots of applications throughout science and engineering. And there is, in our examples, we take a look at a few models ranging from engineering or physics or biology. And a common topic in differential equations is that on the one hand, we can write down a general solution to a differential equation, but in order to get a particular solution, to single out a particular solution from this general class of solutions, we need to specify initial values. So this has been a theoretic introduction into differential equations, and mostly the purpose is to give you a short review of things. And in the next video, we talk more about some applications, and this will in fact lead us again to a number of examples of differential equations. In fact, some of them more complicated than what we discussed here.